Excellent. So we have around 10 people now, and let me do some settings. So no more waiting room. Everybody can join now. Hi, everybody. This is Ray and Racy. We have Jason. Jason, now what time is it now in UK? Is it 7 or 8?
9 o'clock.
Okay, 9 o'clock already.
Yeah.
All right. Jason is actually my, allow me to say it. So Jason is actually my mentee. I know him for, I think, 4 to 5 years because I also graduated from Imperial College. So I realized Jason is a super like a coder because he is in fans of like a different kind of coding skills. And more importantly, is he's really good at sharing. His communication skill is excellent. So I think he already given this sharing functional programming in a CTU, I think maybe 2 to 3 years ago. And that was well received by other students. So that's why today we invite Jason to come and share with us in Out of Hong Kong today, so that more students can actually know why functional programming is important. And having said that, even Facebook, they use Haskell to do like a spam filter. So maybe we would like to know why Imperial College choose functional Haskell, this language, as the first language for university students. Jason is now a full-time staff in maybe a startup company in the UK. So Jason, I pass the time to you. I'm sure you will inspire many of us. Thank you.
Thanks. Okay, so I planned to do this talk in Cantonese, but I'm fine with doing it in English as well. It's easier for me to post this video as well to reach wider audience anyway. All right, so today I'm going to talk about functional programming. Before I start, I would like to ask, how's your programming experience? Have you got any programming experience before? Maybe you can answer in the chat if you wish. How many years of programming experience? Like, what sort of programming languages have you guys used before? Cool. So we have some experience here. That's awesome. I also prepared this presentation assuming that you have no programming experience. So if you haven't had any programming experience, that's fine. You might find some material a little bit advanced, but just go with the flow and see what you can get away from this talk. I'll try to deliver as much value as I could to you. So all right, so let's get started. So today's session is going to be broken down into 1, 2, 3, 4, 5 different pieces. All right. So the first part will do our introduction, just like what we're doing now. And then the second part, we'll talk about functions. What are functions? And how do we do functions in Haskell? The third part is what is lists? How do we build lists in Haskell? And what does it mean? How do we define list formally? The fourth part, I'll talk about recursion. I guess this scares a lot of programmers. I know that many programmers actually are terrified when they see the word recursion, but I'm going to make this fear go away after this session, hopefully. And the last part, I will have some little quiz. I'll have 2 questions for you guys to work on. And throughout the whole session, actually, I'll have a lot of things for you to work on as well. So today, throughout the workshop, oh, by the way, if you have any question, just shout, just unmute yourself. I don't know if you can do that, but feel free to unmute and stop me and talk in the chat. Feel free to do anything to interrupt me. Today we will be using this website, Replit. I don't know if you used it before. You can just go on this link, Replit Languages Haskell. So if I just click on that link, I can also post. Wait, let me just share this document with you as well. Yeah, I'll share this here, and then I'll share this here. Oh, I'm just sharing to Dr. Ray. Sorry. Right. So if you go on Replit, and then once it's loaded on the rightmost panel on the black thing that you see, just type in any numbers and then hit enter and see if you can see what you can see on my screen. So if I type in some number, it should just return the same number. Once you do that, just shout in the chat, just say you can do that. Because this whole workshop rely on this a lot. So I want to make sure everyone has this set up. How are you guys getting on with this? Have you guys set this up already? Does it work when you type in numbers? Yeah, take your time. I've some spare time to let you set this up because this is important. The whole workshop based on this. All right, I'll assume that you have that set up. If not, you can set it up while I do my talk. So the next part that I'll be talking is what are functions. So functions are the basic building blocks in Haskell, and similar to if you have done some elementary school math, you will have touched function a little bit. So in math, we define functions like this, right? Do you see my cursor? Or do I need to do anything to let you see my cursor? I'll try to annotate. Oh, that's cool. Okay, so in math, we define functions like this, right? F, x, and y equals to x plus y minus 2. And when we call the function, when we do f1 and 2, for example, then x and y got substituted with 1 and 2. And the result would become 1 plus 2 minus 2, which is 1. Yeah? So in Haskell, we can define the same function like this. The only difference is there's no brackets and there's no comma. Yeah? There's a very good reason for that. But today I'm not going to cover why, because it's a little bit advanced. So I'm just going to skip it and you just go along with it. You just basically, you don't need to put any brackets. Okay, so next slide. So, okay, now you can already start doing some. So I'll ask you to do the first function right now. So if you go on back to the replit.haskell, I want you to define this function, cube x, where it will return x to the power 3. So the way that we can define, so for example in here, so just now we have that f function, right? F, x, and y equals to x plus y minus 2. Just now we saw this function. When we do f1 and 2, it will return 1 as expected. So you can do similar things to define cube x, and what it should do is should return x cube, basically. Yeah, does it make sense? Oh, okay, great. So let me repeat. Okay. So let me repeat. So in Haskell, we can define a function like this, right? fxy equals to x plus y minus 2. So you can do the same in Replit. So in Replit, on your right panel, you can basically type fxy equals x plus y minus 2. And that would define f in this program. So now f is defined to be x plus y minus 2. So to call it, we can just do f12, which is similar to math, right? Instead, we don't have brackets, f12. And that would call x plus y minus 2 and substitute x and y with 1 and 2. Does it make better sense, Ray? So now your assignment, your task is to define cube x where it equals to something so that it returns the cube of x. Can you post your program? So do not type on the left-hand side. Just type on the black screen that you see. We'll use the left-hand side later. Have you guys managed to get it? Cool. Can you post your solution to the chat if you have done it, so that I know that you have done it? So okay, I'll show you guys how we can do this. Right, the simplest way would be x times x times x. Right, that would be the cube of x. That's the definition. So if we do, once we've defined this, we can call it. We can call it by using the same name cube and then pass in some number, for example, 50. Then it will cube 50. 50's cube is 125,000. Yeah. Yay. Okay. It's weird because I'm used to audience feedback. It's weird, like now I'm talking to myself. Okay, anyway, I'm glad you guys managed to do it. If you have any question at all, just shout it. Don't be shy. Okay, next thing I would like to talk about is conditionals. So all languages, all programming languages has a way to do conditionals. Okay, I'm looking at the question that people posted. So if you follow what I did, does it work? So if you type cube x equals to x times x times x, enter, and then do cube 50, enter. You should do this. You can try it. Okay, anyway, let's move on. So the way to do conditionals in Haskell, there are many ways to do conditionals. One of the most common way, which if you had some programming experience before, you would be familiar with this, which is the if-then statement. So we can define double big number. So we can, this function will return x times 2 if x is greater than 100. Otherwise, it will just return x. Yeah, this is a very simple if-else case. So if we just define that in our Replit again, double big number x equals, if x greater than 100, then return x times 2. Else, return x. And then press enter. And it will load. There's no error. That's good. And then do double big number. For example, 5. It should return 5 because 5 is not greater than 100. So you return x. So if we do double, you can do up arrow to go to the last command. And if we do double big number, for example, 200, then it will return 400. So this is as expected. Yeah. So yeah, this is one way of doing conditionals. But when we stack these if-else to, for example, the second example, mood x. Say if we have some score about a mood x, which is represented with the number x. If the number x is less than 0, then it means the person is sad. And if it's greater than 0, then it means that they're happy. Otherwise, if it's 0, then they're neutral. Then to define this method, you can see that we use two if-else here. The first one is this one. If x is greater than 0, then happy. Otherwise, neutral. And we have the other statement here. If x is less than 0, then they're sad. Otherwise, run this if-else. Yeah, you can see how when this stacks up, it's not very readable. It's hard to read. So in Haskell, there's a way to do this better, which is called guards. So with guards, we can define some condition of which it will execute the expression afterwards. So these two are the same. So we can use if-else or we can use guard. So to test it out in Replit, we'll need to use the left panel. So we can say mood x, right? And then do a new line, do some spacing, and then do the vertical bar. You can find the vertical bar next to your, okay, I'm on the Mac keyboard. You can find the vertical bar next to the enter key. And if you press shift and that vertical bar, you get the vertical bar. So mood x vertical bar, if x is less than 0, then equals to sad. Then if x is greater than 0, then happy. Otherwise it's just next. If it doesn't match any case, it will be neutral. So to run it, we do not press this play button because it wouldn't work. So we can go to the right panel and then type this, load main, and then enter. And what it will do is it will import the function defined in the main. So what we can do now, mood now is defined. We can do mood 50, for example, and then it should return happy. If we do mood minus 50, it will throw an error because we need to put round brackets around the minus 50 so that Haskell know that is a number. There's a reason for that, but I don't want to explain further because it's complicated. But just put a bracket around your negative numbers, and then you get sad. And if mood is 0, then you get neutral. Yeah. Does it make sense? So congratulations, you have written your first Haskell program. Woo! All right, so let's move on. I'm a little bit behind the time. All right, next, pattern matching. Pattern matching is one of my favorite features in Haskell. It doesn't appear in many languages, but it's awesome. So this is a very simple example of pattern matching. So we can write so previously you have seen how we write pattern matching in just how we define function in just one line, right? But we can define the same function in multiple lines and each line can has a different pattern to match. So for example, in this case, +1 unless 0, what this function does is to add 1 to x, the input, and stay, if the input is 0, it will stay 0. So you can see this function is defined in if else like this, but we can use pattern matching to do this conditional instead. So we can type out the function twice, and then it will match the pattern. So this is very similar to God, except it matches the pattern instead of conditions. So if you do this, and then on the right hand side we do load main again, it says okay, and then we do +1 unless 0, and then pass in 0, then it returns 0. Woo! And if we do 50, it returns 51. That's great. Yeah. We're not defining multiple functions. We're defining one function, but with different patterns. All right. I need to be a little bit quicker. So next, it's time for you to try out. So I want you to define this function sin x, which it will return -1 if x is negative, and it will return 0 if x is 0, and it should return 1 when x is positive. Yeah, so go try out. You have 2 minutes to try it out, and then I'll show you the answer. So if you have any question at all, just please shout it in the chat.
Very good, Jason. I think Arnav has a question using the vertical bar. Yeah, maybe you can elaborate a little bit more while the other working on the exercise. Thank you.
Sure. Let me see. I can't find the question. Can you repeat the question to me or post it on the chat, please? So make sure that you have some spaces before the vertical bar. I'm not sure if that's causing the problem, but that's what I do. Put 2 spaces before the vertical bar. And I don't know. I have no idea why it's causing problem for you. If you can show me your code. And also do not press the play button, because the play button will fail. Just on the right hand side, type load main. That's how you load. Okay, great. It worked. No worries. No, I'm not using Visual Studio Code. I'm using Replit. It's a website where you can use a lot of programming languages online without installing anything. So here's the link. All right, time's up. Have any one of you managed to finish this? So let's do it together. So we want to define sin, right? We want to define sin x, and I like using dots because dots are pretty. So if x is less than 0, it's very similar to mood, right? Except it returns -1. And if x is greater than 0, then it returns 1. And then if otherwise, it will just return 0. So if we go back to the right hand side, do load main, and then do sin. Stop! What are the arrows for? And then do sin 50. It will return 1. That's good. If we do sin -50, -5, it will return -1. If we do 0, it will return 0. There we go. We have defined the sin function. I hope you guys managed to do it. So anyway, time is running out, so I need to move on. What are lists? So in Haskell, so we've seen lists before already. Remember the happy and sad? They are actually strings, but strings are actually just a list. So for example, happy is just a list containing the characters HAPPY. And in fact, we can just do a comparison of them. So happy equals, oh my, that's too long to type, okay. Hi, for example, hi is equal to HI, and it's true. So in Haskell strings, this is just a syntactic sugar for writing this. So they're the same thing. So other examples would be just a list 1, 2, 3. That's a list, or other strings, or we can have a list of lists as well. Okay. So let's talk about cons. So the notation just now you saw with the square brackets and commas in between, it's actually a shorthand. So in Haskell, the actual formal definition of a list is actually defined with an empty list and also this magic operator called cons. What it does is it will append an element to the empty list or to any list. So for example, the list with 1 inside is actually a syntactic sugar for 1 cons empty list. Yeah. So if we do in the replit, if we do 1 cons empty list, it will actually return you this syntactic sugar form, list of 1. And if we do 1 cons, 2 cons empty list, we return 1, 2. So what it does is, because 2 cons empty list will return the list with 2 inside, and then 1 cons, and then this will become 1 cons 2. Yeah, so they're all the same thing, but the cons are the actual building blocks for lists. So yeah, so exactly what I said just now in here, the list of 1, 2, 3 is just built from an empty list, and then 3, and then 2, 3, and then 1, 2, 3, etc. So we call this, so this format here is basically the definition of any list. We have X cons, XS, where the XS is a list itself. It doesn't matter if it's empty list or some other list with some things inside. It doesn't matter. But a definition of a list is just X, which is a head. What we call it a head in the functional programming field, and tail is just what's left after the head. So for example, 1, 2, 3, 1 would be the head, and the list 2, 3 would be the tail. Does this make sense? If not, you can ask me any questions in the chat. Next, it's time for you to try out. So on the rightmost panel, I want you to write FF in the simplest form. So I want you to write out, for example, 1, 2, the simplest form of 1, 2 is this. So I want you to do the same for FF. So what would be the simplest form for this? Correct. Yes. Whoa, that's perfect. Yes, correct. That's the answer by Jane is awesome. Yeah, that is the simplest form of FF, correct. So we have a character F, cons with the character F, cons with an empty list. Okay, UT, thanks UT. That's perfect. And that will give you FF. That's awesome. Next, I want you to write out, if you have time, if you want to try out yourself, you can write out the simplest form for this. It's a little bit more tricky, but I believe you can do it. So let's move on. Next, now we know about the structure of a list. We know what are the definitions of a list. Now we can actually destructure, not destructure. We can actually pattern match lists as well. So before we have seen how we can pattern match 0. Now we can actually pattern match with lists as well using the cons operator. So for example, in here we have head of list, which we destructure it. So we have the head part and the tail part. So you can rename head and tail to anything. You can have x cons xs, it doesn't matter, and then equals head, which returns the head. So what you'll do is, for example, head of list 39, 5, and 4, it will return 39 because it is the head. Because this list breaks down to, okay, so here it explains how it works. So this list breaks down to 39 cons, 5 cons, 4 cons, empty list, right? So to pattern match it, x becomes 39, and then xs becomes the rest of the list, which is 5 cons, 4 cons, empty list. Yeah, and then we can just return the head, which is the x. Yeah, it's so cool, right? It's the most amazing thing about Haskell. Okay, now it's your turn. I've got many hands-on for you. So I want you to define a function similar to head, but it returns, oops, it returns the first two elements in the list. So if they exist. So for example, first two empty list would return empty list, and then first two 3, 4, 5 will return 3 and 4, the first two elements in the list. So try it. First two. I'll show you here. Yeah. If you guys have the answer, feel free to post it on the chat. It's good that we share with each other. So the way to load your program is load main. It will load your program into your interactive panel. All right, so let's try to define this. So first two takes in x. So it takes in a list, right? So what we can do is we can pattern match the list by doing x, which is the first element, and we can further pattern match the tail. So we can do x, y, and then the tail. Oh my god, tail is a name. Okay, xs. Then it will equals to. So what we want to return is just xy, right? So this should do the work. This should do the job. If we load main, and then if we do first 2, 1, 2, 3, it will return 1, 2. But problem comes when the list is smaller than when the list is smaller than 2 elements. You can see it throws an error. It says non-exhaustive patterns. The reason is because it doesn't. This array here doesn't match this pattern. Yeah, because here we say that we'll match any list that contains at least 2 elements, right? So the way to do this is we can have an extra case here. If it is an x cons xs, which means, actually we need to define here. If it's x cons xs, then return just x. And then if it's an empty element, just return empty. I think that might work. Oops, I forgot the brackets. Cool. So if we do first 2 empty list, we return empty list. If we do 1, we return 1. That's good. 1, 2, we return 1, 2. So the reason that we put this pattern at the end is because otherwise, if we put this here instead, all the lists with 2 elements also match this pattern, so it wouldn't work. So if we do this, so I can show you. Oh my God, what's going on? Oh yeah, great. The compiler even knows about it, and it says the pattern is overlapping. That's great. So you can't even do that. So you need to put it at the end. So, yep, that's it. Is there any question? I see many arrows. What are the questions? Shouldn't we use the init keyword for this? I don't know. I don't know what the init keyword do. I'm not sure what you're asking. So yeah, I don't know. So let's go back to the presentation. So we have some predefined functions for lists. For example, plus plus, we pronounce it as concat. So it concatenate 2 lists. So for example, 1, 2, 3 concat 4, 5, 6, it will return 1, 2, 3, 4, 5, 6. And then head is just like what we defined just now. It returns the first element in the list. Tail, it returns the tail of the list. Length, it will return the number of elements in the list. And we have many more. Next, what is recursion? Finally, we come to this part. Okay, have you guys got any question up to this point that I can clarify for you? If not, I'll continue. You have 5 seconds to ask the question. 5, 4, 3, 2, 1. Okay, let's go. Okay, recursion, my favorite part. So there are many things that are recursive in the world. For example, Russian dolls, they're recursive. Try to refresh your page if load main doesn't work. Make sure you have colon as well before load. So there are many things that are recursive in the world. For example, Russian dough, you know how you have you have a dough inside a dough and then inside a dough, and it never ends. And for example, broccoli, like I can never tell if you cut this part of the broccoli and photograph it in a scale like a broccoli, it's the same thing. So this is a recursive structure. And for example, on the right hand side we have the Droste, I don't know how to pronounce that, but it's a chocolate drink powder thing. And as you can see in the picture, it actually has the can itself and the picture of itself. So this is a recursion as well because it refers to its own thing. So this is what recursion is. It refers to it. The definition of something is based on itself. Let's see. So here's a joke that people always make about recursion. If you want to understand recursion, you need to understand recursion. See where the joke is, because understanding recursion is recursive. Okay, anyway, I find it very funny. So actually, we have seen recursive structure already previously in Haskell. So remember how the simplest form of any list is an empty list, and we have cons which add things to the list. For example, a list of number can be defined as, so we're defining now a new type. We're calling number list is either an empty list or a number cons a numbered list. So this is where the recursion occur. So number list is defined by itself. So what this means is we can now prove something is a number list. So for example, if we want to prove 1 cons, 2 cons, empty list is a number list, we can first say that, okay, an empty list is an empty list is a number list by definition, by this definition here, right? And the second part, so therefore, 2 cons empty list is also a number list. Yeah, because on the right hand side, the definition says number cons number list is a number list. And because we've proven empty list is a number list, so 2 cons empty list would be also a number list. And at last, we can prove that 1 cons, 2 cons empty list is a number list, same way as how we proved it before. This is a very kind of informal proof, but it works like that. If you're interested in reasoning about programming or this sort of theory stuff, this sort of stuff is what you do. But yeah, anyway. So next, we can even prove further. We can prove A cons all the way to N cons empty list is a number list by doing the similar thing that we did before. But you can see, as we want to prove a larger list, it requires more steps in the procedure. And that's not nice. So we can simplify this. If we notice, the step 1 to step 5 are actually a proof itself. From step 1 to step 5, we can prove that B cons, C cons, all the way to empty list is a number list. So what this means is that we can actually write this proof in a simpler form. We can first prove B to N to empty list is a number list, and then voila, we have our proof for A to N to empty list because we have proved that B to N is an empty list, and then now A cons some number list must be a number list. Yeah. So this proof is itself a recursive proof, which is great. Any question? Okay, this part is a little bit more academic, but let's look at more academic stuff. Okay, it's important to understand the recursive structure before doing recursion. Otherwise, what are the arrows for? Are there any questions? So if you understand the recursive structure of things, then you can iterate through them efficiently when you actually get your hands on recursion. So I'll talk a little bit more about recursive structure. So numbers, for example, 1, 2, 3, 4, 5, they are also in a recursive structure. So we can define all natural number with 0. Yet this is not failed Haskell. I'm just talking about recursive structure. This is a concept to understand. It's a more scientific or mathematical law concepts. If you understand the recursive structure, then you will understand how to do recursion better. Yeah, good arrows, because that part that we refer to number itself, right? So all the natural number can be defined by 0 or 1 plus a number, right? So we can prove that 56 is a number by saying that, by doing the same thing that we did before, we can prove 55 is a number. And because 56 is equals to 1 plus 55, therefore 56 is a number. Yeah, it's super trivial, it's stupid, I know, but it's important that you know the structure about each number can be deconstructed into just 1 plus 1 plus 1 plus. So if we write out this proof, it will become this. So 56 is just 1 plus 1 plus 1 plus 56 times plus 0. And that would be a number. Yeah. So now we understood a little bit more about recursive structure. Now we can talk about recursive functions. For example, if we want to define, previously we've done the cube of x, which is defined like this. What if we want the 24th power of x or the 50th power of x? Then we will need to write out x many times, right? That's not very nice that's not efficient. So maybe we can define this function called power xn, which returns x to the power n. And we can write this out like this, but it's not possible to, because n varies, right? So in Haskell, we can just write power xn equals to x times power xn minus 1. So what this is doing now is, notice that x to the power n is basically equals to x times x to the power of n minus 1, right? Yeah. So because of this property, then we can write the same thing out in Haskell. So power xn is equals to x times power x n minus 1. So let's try it and wrap it and see what happens when we run it. So if we do error power of xn equals to x times power of x n minus 1, define this. And then if we do power of 5, 2, you can see it runs, but it never ends. So, okay, it actually, okay, we need to stop it. Okay, it never ends because there's a, yeah, that's right. We have an infinite recursion. The reason is because it doesn't end because we need a base case for this. When n reaches 0, that's great. Thanks you. Yeah. So what we need to do to fix this is to define a base case, a case where it is so trivial that we know the answer. So power of x0, for example, we know that anything to the power of 0 is 1. We can just do this. So with this, now we can see as n goes smaller and smaller, it will reach 0 at some point, and it will return 1. So if we define it here, and then do load main, and then do power 2 to the power 3, return 8. That's correct, according to my quick math. Right, awesome. All right, let's move on. Hopefully you guys understood it. Next, we can define this function size. So size xs will return the number of elements. So we can define this in Haskell through pattern matching. So size of an empty list will return 0, and we can pattern match. If it's not an empty list, then we can get the head, and then it would just be 1 plus the size of the tail of the list. Yeah. So this is all coming from the recursive structure that we learned before. Cool. Now, is there any questions before we start the quiz? So I have a quiz for you prepared. Do you have any question about recursion or anything? So I would like to also, yep. Is there any question? I'll also like to mention something about how to think about recursive function. So when you want to define a recursive function, a tip would be first, well, usually people say think about the base case first, but that's not what I agree. I think you should think about the recursive case first. Think about.
Sorry, Jason, just to interrupt.
Hello.
I noticed there's a member here keep on putting the annotation on the screen. 同學仔啊，麻煩大家唔好寫字喺個 screen 嗰度嘛，咁會影響其他人。Can you not doing this, or you'll be removed from the group? Okay, please note. Jason, please continue.
Okay, cool. Yeah, so I was talking about some techniques that I use to create recursive functions. The first one is do not think about the base case first. Think it last. That's just my personal tip. People usually say otherwise, but yeah, you can see whatever fits you. Second is to solve the problem as if you already have the problem solved. So for example, in this case, power xn, let's just assume that power works already. If power already works for any x and n that is smaller than the input, then we can just have x times power of x n minus 1. Do not think recursively. Do not try to expand it. Just trust that. Just have some faith in yourself. Trust that this power x n minus 1 is going to work just like how you expect it to. Then it's much easier to define recursive function. All right. I assume there's no other questions because I haven't seen any. So here's the quiz. There are two questions. The first one is to define the function sum xs, which will return the sum of all the numbers in the list xs. The second question, oh, I didn't change this, factorial x, which returns the factorial of x, which is x exclamation mark, which is x times x minus 1 times x minus 2 all the way to 1. Yeah, so here are the two questions that I have for you. Spend your time until the end. I'll quickly show you guys how we could do these two. And do post any question if you have any. Okay, looks like sum is already a keyword, so just add something, my sum or something, so that you can define that. All right. So let me quickly just go through how you can define those two functions, right? So to define sum, we can think about what are the input, what are the recursive structure of the input. So we have a list of numbers, right? So list of numbers, we can destructure it. We can I keep saying destructuring. Okay, we can pattern match it with. We know a list is either an empty list or a head with a list, right? So we can use that. So if it's an empty list, so let's think about the recursive case first. So if we have some list, right? The sum would just be x plus the rest of the list, right? To get the sum of the rest of the list, it's just my sum and then xs. And we don't know if that works, but if my sum works as expected, this whole expression makes sense because my sum will return, it promised me that it will return the sum of xs. And if we have the sum of the tail, we can just add the head to the sum of the tail to get the answer. And then now next step is to think about the base case. So what is the most basic structure of a number list? It's just empty list. If it's an empty list, then just return 0. Yeah. So we go back here, load main, my sum 1, 2, 3. That will return 6. That's correct. 1 plus 2 is 3. 3 plus 3 is 6. Yay. Next, we need to define size. Oh no, factorial. So, so think about the recursive structure of a number again. So a number is just either 0 or 1 plus some other number. So what we can do is factorial. Factorial of x is just going to be x times factorial of x minus 1. That's the definition of factorial, right? X factorial is equal to x multiply x minus 1 factorial. Yeah. So again, you can reason about this. So assume that fact already do what you are planning to do. Then fact x minus 1 will return the x minus 1 factorial. And with that, we can just multiply x to it. And then now think about the base case. The most basic structure would be 0 for a number. And 0 factorial is, what is 0 factorial? I don't know actually. 0 factorial is 1. So 1, there you go. So we have defined this. So if we load main, and then we do fact 5, we return 120. That's correct. Yeah, so just in time, I finished all the slides that I've prepared. I hope you guys have something to take away. Don't worry if you still feel confused about using Haskell or anything. I hope at least you were able to like get something out of it. Yeah, thank you.
Thank you, Jason. I think you give us a very important like overview about what is Haskell. Having said that, most university students, they learn Haskell for like Imperial, maybe 10 weeks and a lot of weekly assignment. And in this hour of code lesson, I think just about like a simple function can be for 1 week. But I think Jason is actually putting like a few weeks exercise putting together in 1 hour. Maybe we may have some difficulty to understand everything, but we have recorded the session, and I think the slide will be also shared online. And I hope everybody can understand Jason is giving us a very crash course about what is a Haskell functional language, and that will give us a good start to keep learning this language. Jason, how are you doing recently? Okay, good. I would like to like share one screen because recently you have this photo. I would like to see if I can share the screen. Actually, maybe not. What I can do is yeah, I think I can share. So what I will do is this. Okay, I share one of your photo. Let me see if it works. So in this photo, what you can see here is, I think everybody can see, this is a photo. Maybe Jason, you can let us know what this photo is about. So you were in this, you can mute. All right, let me speak it. So I think everybody can see this photo. So Jason is actually in London at the maybe like an auditorium, and then he's presenting a language called VUE. And he's a very serious coder. And again, I mentioned he's a very serious musician. So he's applying his musical knowledge together with coding to develop very interesting like a piano, a keyboard, like an application. So as a good coder, we don't limit ourselves to one particular language. We should be able to pick up many different languages. But again, you need some of your strong interests, your passion, and some good domain knowledge. And together you will become very successful. So I hope with the lesson today, most of us can understand learning coding is a long journey, and there's so much we can do together. Our Code mission is to raise the awareness of coding, computational thinking for Hong Kong citizens, no matter who you are. We hope today there will be some university student and high school teacher. They are all joining us. And Jason, we hope you can continue and share more with us. That's all I want to add on to the end of the sharing today. Thank you. We really appreciate that. Bye-bye, Jason. Keep in touch. Okay, bye-bye.